so he's familiar with German system because he was a postdoc at MPIA, so Max Planck Institute for Astronomy in Heidelberg from 2017 to 2021. And his current position in Rome is funded by ERC Synergy Grant, led by Sergio Molinari in Roma, Ralph Klessen in Heidelberg, Patrick Enebere in Paris. So these are all the places he's been to. And then Leonardo Testi, who of course you know very well, he was at ESO until recently, and he's now professor in Bologna. So it's all connecting all the dots. Yeah. So Juan is an expert. As you hear from his talk today, Juan is an expert in observational and interpretational study of the interstellar medium, mainly using observations in radio and microwaves. Also in today's Jack, he will tell us about his recent findings and insights into possible origins of filamentary structures in the ICM. This is very beautiful, seen in both 21 centimeter and CO emission. Let me also say that he's also an enthusiastic science communicator. So especially students who are also similarly interested in that kind of thing, have a passion for it, here's your opportunity to really ask him how it goes, that kind of aspect of his work after the Jack. With that, Juan, please.
Thanks very much, Eiichiro, and thank you all for being here this afternoon. So there's a very broad range of scales at this institute here in Garching. And I'm very happy to say that we're all linked together by hydrogen. So before we enter into the talk, I'm going to just briefly flash my collaborators, mostly from the THOR collaboration and EcoGal. And let's start with this. So this is the star that you see in the sky of Munich when the sky is not optically thick. So this star, the sun, is responsible for most of the forms of energy on Earth. It's mainly made out of hydrogen. Our universe, the baryons in the universe in the form of atoms are mostly hydrogen. So that's something that links us through the broadest range of scales in the universe. Our own galaxy is composed of stars, dark matter, and gas. And most of that gas is in the form of hydrogen, and particularly in the form of atomic hydrogen. So just hydrogen atoms flying around. 60% of the hydrogen in our galaxy is in the form of atomic hydrogen. So today I'm going to tell you a story of that hydrogen, how that hydrogen cools down, gets shielded from external radiation, forms molecules, eventually cools down enough that enhances gravitational collapse to form stars, how those stars explode and bring back some energy and momentum into their surroundings, and they close the loop that we know as the mass cycle in the interstellar medium in our galaxies and similar galaxies. Okay, so I'm not going to assume that you know anything about atomic hydrogen, and maybe you don't even care, but I'll try to tell you the story as seen from hydrogen. So I'm going to tell you about the hydrogen, but first I want to see a show of hands. How many of you have seen the atomic hydrogen towards the Milky Way? Raise your hand if you have seen it at least once. Okay. Well, I mean, we have no radio eyes, so yeah. Okay, so like 50%. So I'm going to show you, ladies and gentlemen, the atomic hydrogen towards the galactic plane. So this is the galactic plane of our Milky Way, as seen by Gaia. Here you see extinction from stars. And then we're going into a section of the galactic plane. And then we change into radio eyes. And then we'll see this. If you assume circular motions around the galactic center, you can actually assign a distance to each one of these velocity channels. What you're seeing is the Doppler shift of the 21 centimeter line. This looks like a mess, doesn't it? So the talk today is going to be about how to make sense of that mess. And it has two big parts. First, I'm going to tell you what do we learn from that mess, that is the atomic hydrogen emission towards the galactic plane. And second, I'll tell you what did I do with that particular mess. Okay, so those are the two main parts. If you have any questions, if you have a very pressing question, just let me know and we can interrupt. But if not, we can talk at the end, okay? So let's begin. So everything starts with radio astronomy. So the discovery of radio waves coming from the sky by Karl Jansky at the end of the 20s. And then the history of the 21 centimeter line. It's a very troubled history. it goes more or less like this. This is 1945, as you know, it's a very complicated year. In 1942, Marcel Minert, that was a professor at the University of Groningen, knew that Nazi Germany was invading the Netherlands. And he, being a member of the Communist Party, knew that this was very bad news. So he sent his very talented student, Henrik van der Holst, to work with Jan Oort, that was hiding himself because the Nazi troops were looking for him to make him work in the radar. So Oort was working at 100 kilometers from Leiden and commuting to Leiden only on Saturday nights to talk to van der Holst. And the result is the work that I'm going to show you. And it's the prediction that the hydrogen atom has a transition that comes from the change in the spin of the electron with respect to the spin of the proton. Back in the time, they estimated that that calculation was very unlikely, that this line was most likely not measurable. So the atomic hydrogen was not for sure going to be observed, and it was only in 1951 where the first detection was made. As you can see, it's a box antenna, so a very large beam, 12 degrees in the sky. The first estimation of the correct, the Einstein coefficient for the H1 emission comes from Ukrainian scientist, actually, Joseph Shkokowski, and I have no idea how this paper made it to the States. The origin is in Russian, so if you know anything about the history of 20th century astronomy, please tell me how this paper arrived. But the point is, H1 centimeter was measured in the States first, and then in the Netherlands, the radar antennas were refurbished as radio observatories. And they were used to produce the first observation of the atomic hydrogen towards the Milky Way. So this, what you're seeing, is the first survey of atomic hydrogen towards the Milky Way. So here in the x-axis, you're seeing galactic longitude. So we're going along the spine of the Milky Way, and we're moving at 2-degree beam. That is the beam of that 7-meter antenna. And in the y-axis, what you're seeing is the Doppler shift of that line. So here you're seeing the Milky Way rotating. You're seeing that the line is displaced up to 120 kilometers per second. Here's the galactic center. By the way, if you see pink lines, it's me putting graffiti in historical plots. So here's the galactic center, and then you see the inner galaxy, then it goes away, and then goes to 0. So 0 is the local, the local standard of rest. Okay, so far so good. We have a measurement of the atomic hydrogen emission towards the galactic plane. The next thing that you can do is just try and reconstruct how the Milky Way looks face on, because we happen to live in the galaxy, so it's very hard to reconstruct it. So something that you can do is assume circular motions around the galactic center and try to produce a reconstruction of the Milky Way face on. So this is the first reconstruction of the Milky Way seen face on by assuming rotational motions. These kind of reconstructions are extremely controversial. And the reason for that is that we know we are not simply dominated by circular motions around the galactic center. Even if we were, looking at the center and the anti-center is very difficult because then your circular motion component is minimum. So most likely you're dominated by drift or some other kind of motions. So we have been taking these maps with a grain of salt, although some people claim that they have seen spiral arms. So this is a family of models. All I'm going to say is these reconstructions are complicated and are hindered by the fact that we're converting velocities into positions in the sky. We know that that is difficult in the outer galaxy because a parcel of gas can happen to fall in, parcels of gas that are separated by many parsecs, hundreds of parsecs, can fall in the same velocity channel. You have drift motions, and towards the inner galaxy, you have ambiguity. The same velocity actually represents two different distances. How to separate those different distances? There's no clear strategy to separate that. So I'll say, take this with a grain of salt, and what I can tell you is that other galaxies also have spiral arms in H1. And the H1 spiral arms extend much further than the characteristic radius of the stars. So the spiral arms in H1 go much further away. Okay, so that's one thing. Milky Way, seen face on, spiral arms, we don't know, maybe. The other thing that we learn is that our galaxy is not flat. Our galaxy has a warp. So that means it's going up in one side. So here it goes up to 6 kiloparsecs. And in the other direction goes down to 2 parsecs below the midplane height. And then it goes up again. This is what is known as the Milky Way warp. So our Milky Way is not flat. It's more like a potato chip. What is producing that warp? We don't know yet. We have many ideas. None of them is conclusive. This is the latest version of the warp from my own work. So here you see it very clearly. Here in red, we go up to 3 kiloparsecs. I don't extend as far as the other work that I was showing you. And here we go down. So this is the galactic center. Here the galactic center is towards the, the galactic center is towards the bottom. And is towards the first quadrant that you have the galactic plane going up. And towards the fourth and third quadrants, the galactic plane goes down. So we have spiral arms that we don't believe. We have a warp that don't know where it comes from. But we also have something else. We have a flaring. The characteristic height of the atomic hydrogen changes with galactocentric radius. It goes from around 1 kiloparsec to up to 6 kiloparsecs in the outskirts of the galaxy. So the galaxy is not only slanted like this, but it's also opening up. This is consistent with hydrostatic equilibrium. So you're going to have some of less pressure in the outskirts, and this is going to flare. Still, it's observed with more recent data. This is from my own work, and the warp is on top of this. So besides the slanting, the disk is opening on the side. Okay, so we have spiral arms that we don't believe, a warp that we don't know where it comes from, and a flaring that most likely comes from hydrostatic equilibrium and the fact that you have less pressure in the outskirts of the galaxy. What else do we have? We have a mess. So this is the first color image of that mess. This is from Carl Heiles that used a projector and some commercial film to take pictures of the first H1 map. So here what you're seeing in color are different velocity channels. So you're seeing red in 20 kilometers per second and minus 20 kilometers per second in blue. And the first thing that struck Carl Heiles' eye is the fact that you see cavities like this one, and like this one. And we know now, or at least suspect, that these are bubbles. In H1, we see many structures which are shaped like a circle. And if you take a profile, they have a double line profile towards the center, such that you see, in principle, the back and the front of that cavity. And if you make a radial profile, that double profile becomes a single profile. So you can calculate the expansion velocity of those bubbles, most likely coming from supernova. And because of their size, they cannot come only from one supernova. Most of these bubbles have sizes of the order of 100 parsecs, 50 parsecs. So you need several supernova. So one supernova delivers 10 to the 51 ergs. You need 10 to the 53 ergs to blow a bubble that is around 100 parsecs in diameter. So we also have those ones. So people have tried to make catalogs of bubbles. So this is one of the biggest examples of that one. This is from Leroy and Paulus, where they see, for example, this one, the Orion-Meridiana superbubble, and many bubbles towards the galactic plane. The catalog of bubbles is extremely incomplete because by definition, you're only seeing the very late stage of the supernova remnant and only the ones that are kind of nicely distinguished from their background. But still, we know some things. We know that there are more bubbles in the inner galaxy. So here the lines correspond to bubbles that have been identified in H1 observations at different resolutions. And here is the profile of star formation of the Milky Way. So we know that the star formation in the Milky Way changes by 2 orders of magnitude from 5 kiloparsecs to 15 kiloparsecs from the galactic center, and we see less and less bubbles. It can be the case that bubbles that are further away are difficult to see, but we also know that it's less likely that we have many high mass stars out there to explode a supernova, and even if we have them, they have to cover a larger volume. So it's normal that we see this profile. So we have a spiral arm structure that we don't believe. We have a warp that we don't know where it comes from. We have the flaring that is most likely hydrostatic equilibrium. And then we have a bubbling interstellar medium due to the explosion of supernovas. Okay? What else do we have? We have weird lines. So one of the first things that came across, people came across is that the H1 line, in principle, is not only Gaussian, but sometimes it has these dents. Like this one. Where is my pointer? Like this dent. Oh, great. You cannot see my pointer, but you can see this dent up here. It's not only described by a Gaussian, but sometimes that Gaussian has a little dent. And the interpretation is the H1, in principle, if you calculate the cooling and the heating in interstellar medium, the H1 comes in 2 flavors. A warm flavor that is 1,000 Kelvin and a cold flavor that is more like 100 Kelvin. Sorry, 10,000 Kelvin and 100 Kelvin. So if you see a cold cloud, one of the clouds that is a few tenths of Kelvin in front of the hot background, it would look like those dents in the spectrum. So what do we know about the H1? Well, spiral arms that we don't believe, warp that we don't know where it comes from, flaring, bubbles, and now it comes into flavors. It has multi-phase structure. So what have we been doing with that? Well, it turns out that 21 centimeters is a very long wavelength. It's very hard to observe high resolution in 21 centimeter. The Arecibo telescope and actually FAST are the largest single dish telescopes that are used to observe 21 centimeters, and they give you a 4 arc-minute resolution. The largest one that we have that is steerable, so one that you can actually point in the sky, is Effelsberg, and it gives you 10 arc-minutes. If you want to go further, either you build a telescope that is larger than Arecibo or FAST, or you have to go to interferometers. So with interferometers, people have been pushing the limits to 1 arc-minute. So if you work in the visible, please don't laugh, because I know that 1 arc-minute is very broad for you guys. Probably a whole universe fits in 1 arc-minute. But that was pretty awesome because we started to see very interesting stuff. For example, remember that dent that I showed you in the spectrum? Actually, there are whole clouds that look that are revealed by that dent. So here you see in the contours the CO, and here in grayscale you're seeing the H1 emission. So this shadow is not decrease in emission; is the absorption. This is a cloud of cold hydrogen that is seen against a hot background. So we see some of them are matching with the CO. Actually, the ones where we really know that is a HISA, H1 self-absorption, are the ones that are matching with the CO. But also we see some that only have H1 so far. Some of them have OH, but most of them have only H1. So this is cold atomic hydrogen that is also in our Milky Way. How can we push this even further? Well, you use another configuration of the interferometer. You extend your antennas even more, and then you construct the highest resolution galactic plane survey of the Milky Way. And that's what I did, what we did in the THOR team. So this is a project that was led by Henrik Beuther, and we made a map of the H1 emission towards the galactic plane in high resolution that looks more or less like this. So again, we couldn't cover the whole galactic plane because we're in the northern hemisphere, and also we don't have infinite time. So we just cover a portion of the first quadrant. So here we're moving into the inner galaxy. We have a band of plus and minus 1 degree in galactic latitude. And here we're moving in galactic longitude. So unfortunately, the quality of the video is not great through Microsoft Teams, but you're going to see the beautiful mess that I work on, but also you see those dots. Those dots are strong radio continuum emission. Those are galaxies that are behind the Milky Way that we can use to constrain the optical depth of the H1. There's also some radio continuum emission coming from the Milky Way in the form of H2 regions and supernova remnants. And all of those are there. So what did we learn from this survey? Well, this is the LB diagram. So this is, again, galactic longitude and velocity. We learned that the H1 is not optically thin everywhere. So using those strong radio continuum sources, we construct a map of optical depth in the Milky Way. So what you're seeing here is longitude and velocity, but here you're seeing galactic latitude and galactic longitude. And what you're seeing with the colors is optical depth. So it's in these weird units, but this is telling you that it's not constant. You have some more optical depth or some lines of sight. And actually, if you correct the optical depth that we always assume is less than 1, we assume that H1 is actually optically thin, we derive that actually we have been off in the mass of atomic hydrogen by a factor of 2. So we're closer to 10 to the 10 solar masses in atomic hydrogen. And that atomic hydrogen has been hiding in places where you have, is mostly in this side of the distribution. At high column densities, we have more atomic hydrogen than we expected. The other thing that we learned is that there are HISAs everywhere. So right now, I hope this video works, because if it doesn't work, it's kind of lame. Okay, so here, this is a supernova remnant, but here you see in the H1. Here you're seeing the CO. So we try to match the CO with the H1. So if you take the THOR survey, which is 50 degrees in the galactic plane, and you look at each velocity channel for 1 second, in tiles of 1 degree by 1 degree, it would take you 8 hours to look at the data. So I'm not intending you guys to do that here. But when we match, we develop this algorithm that matches the shape of the H1 and the CO, and we discover that the H1 and the CO are co-moving and co-spatial. So we find places where the CO and the H1 are moving together. So there's H1 that is coalescent with the molecular clouds. There's H1 in the molecular clouds. It's not only around, it's also inside. And it looks like this. So this thing that looks like a shadow here actually corresponds to this molecular cloud here. I'm going to show you back and forth until you get tired of me doing this, and then we can move to the next slide. Okay, so what else can we do? So remember, we were looking for bubbles, we were looking for spiral arm structure, warp, flare. What else can you do with the atomic hydrogen? Well, it turns out that something that is visually striking is the amount of filamentary structures that appear there. And filamentary meant stuff with a large aspect ratio. You see lots of sticks. You see them here, you see them here, you see them here, here. Even in the supernova remnant, there are sticks. So a stick seems to be like a natural way to describe this data. So that's what we did. We turned the sticks into something that hopefully would tell us about the galactic astrophysics. But in the beginning, we just wanted to learn about those sticks, what they are and where they are and how they behave. So how do you turn a scalar field like the intensity across velocity channels into sticks? Well, we use the Hessian matrix. It's not the only method. There are other methods. There's this Peirce, there's the Rohlenhoff transform. This one has the ability of being really fast because we needed to do this a lot of times, and also it's interferometric images. So we needed to be very sure that the noise of the interferometer was not causing spurious filaments. So we needed to do this fast and again and again. So a scalar field of emission looks like this when you plot it in 3D. And then you can calculate the curvature using the Hessian matrix, which is the second order derivatives of the intensity field. Then you can calculate the eigenvalues of the Hessian matrix, and one of the eigenvalues gives you the direction of the longest, of the elongation of those high aspect ratios structures, okay? So that is what we did. So we turned our, we did it tile by tile and velocity channel by velocity channel. So we split our data in tiles of 2 degrees by 2 degrees. We turn them into that eigenvalue that highlights the structure. This doesn't really point, so I'm just going to assume that you guys are going to be looking at what I'm pointing with my hand. So here in the middle, you see the filaments that are highlighted by the Hessian matrix. And then in the last panel, you're seeing the angles, okay? So far, I'm going from emission into filaments into angles. So we're not reducing the dimensionality of the problem. Probably I'm just making you dizzy by showing you angles. So you can do a histogram of angles. So for example, oh yeah. Or, well, I don't think I have more panels like this. So you can do a histogram, for example. So for one particular tile, we saw, sorry? This is the angle of orientation of those structures to the galactic plane. Yeah, sorry, yeah, to the galactic plane. So blue here means mostly parallel to the galactic plane, and gray means mostly perpendicular. So this guy is perpendicular to the galactic plane, and here blue is parallel to the galactic plane. You can make a histogram for that particular tile, and 3 velocity channels. You see that actually these 3 channels are peaking around 0, so these are mostly parallel to the galactic plane. Again, a histogram is not a very good way of synthesizing that information, but you can do a spectrum. So you have the spectrum of intensity that you see in the top channel. You see how difficult it is to decompose the H1 spectrum into Gaussians because it has all of these bumps. And then you can make a spectrum of angles, okay? So here you're seeing that most of the angles are 0 degrees. Most of the structures in this particular tile are parallel to the galactic plane. It turns out that working with angles is tricky because your error bars are hard to determine because it's a circular distribution. So imagine that you wrap a Gaussian around a circle, so then there's a limit to the width of that Gaussian. So the correct way of estimating the uncertainties in that angle is using something that comes from the field of circular statistics. So imagine the random walk problem, okay? So if you're not familiar with the random walk problem, you go to a bar tonight and then you drink as much as you can. Then you go out and then you measure how far from the bar you arrive. And then you're doing physics because that's the random walk problem. So we assume that each one of the filaments is going to correspond to one step in the complex plane. So if all of the filaments are parallel, you're going to have a long displacement in one particular direction. If the filaments are completely randomly oriented, you're not going to go too far from the center. And in reality, you're going to have something in between. You're going to have a combination of a long displacement and some randomness. And the way to quantify that displacement is called the projected Rayleigh statistic. So the projected Rayleigh statistic is not more than the projection of that displacement in one of the axes of the complex plane. So here I'm folding it by 2. So I'm going to be sensitive to 0 degrees, parallel to the galactic plane, and 90 degrees, perpendicular to the galactic plane. And this is the equivalent of a sigma for a circular distribution. So if you see positive sigmas, that means the significance of mostly parallel to the galactic plane, and negative sigmas, or negative V, significance of perpendicular to the galactic plane, okay? And then there's the weight that is related to the fact that we have a beam. So not all of the gradients that we have are going to be independent. We have to account the fact that you have some correlation in your gradient observations or that we use to calculate the Hessian matrix. Okay, so how does that look? It looks like this. So for one particular tile, you see that we have up to 8 sigma of preferentially parallel to the galactic plane. So this is just for one tile. Now for the whole galactic plane, this is how the emission looks in those 2 by 2 degree tiles. But then this is how it looks in orientation. So we have mostly parallel structures to the galactic plane, and then some places where you have concentrations of structures that are vertical, perpendicular to the galactic plane. The significance of this tendency is shown here. We have a very high significance of the mostly parallel structures, less of a significance of the mostly perpendicular, but still very significant patches of the structures that are vertical and perpendicular to the galactic plane. So what is happening here? We have some filaments parallel to the galactic plane, some other perpendicular to the galactic plane, and it kind of looks like this. You're going to have a distribution. It's not that you see all of the structures completely aligned, but you have mostly horizontal here, for example, and here you find these verticals, and then this is this white patch that you see here, and then this is mostly parallel, okay? But you have a whole distribution of filaments. It's not that you see them all being parallel to each other or to the galactic plane. How can we interpret that? Well, first we have an oddity. We found something extremely weird. So weird that we put it a name. So this is the Magdalena filament. I'm Colombian. I name it after the longest river in Colombia, the Magdalena River. And of course, English speakers baptize it Maggie, but it's okay. Maggie is in that section of the galactic plane where the disk warp makes the galactic disk go up. So actually this structure, this elongated structure, is 500 parsecs below the galactic plane. So this is the first weird thing that we found. So this is the work of Jonas Seid, that is a PhD student in our group in Heidelberg. And this is made out of mostly cold hydrogen. So the line widths are kind of narrow, and you can distinguish it very well from the background. So this was an oddity, that's why we put a name, but we also have to deal with all of these horizontal and vertical filaments. The interpretation for this came after we did it for the whole galactic plane. So now we sacrifice resolution. So we had the highest resolution galactic plane map. Now we go in lower galactic resolution, lower angular resolution for a bigger patch of the galaxy. And what we found is the following. So this is how that data looks. And what we found is the following. We found this LB diagram. So we found some bands of red and some bands of blue. And probably you can recognize it better if I fold it like this into a galactic plane. Most of the red is in the outskirts of the galaxy. Most of the blue is in the inner galaxy. In the inner galaxy, we have the ambiguity of near and far. So for the sake of simplicity, I just put it in the far side. Or something else that you can do is you can make a profile of the orientation with galactocentric radius. What we found is that for filaments in the inner galaxy, the tendency is for them to be perpendicular to the galactic plane. Here, each dot corresponds to one tile. So if you want to enhance the significance, well, you can add these ones in quadrature, but in principle, the profile doesn't change. You go from mostly negative, so mostly perpendicular filaments, into mostly parallel filaments in the outer galaxy, and then it flares out kind of everywhere. Okay? So how can we explain that? How can we explain the fact that in the inner galaxy, most of the filaments tend to be like this, and in the outer galaxy, they tend to be like that? Well, one plausible explanation comes from how they look. So these are filaments in the inner galaxy. So you see some of them actually are coupled in bubbles, but some of them seem worms that are crawling out of the galactic plane. That is not my phrase, that is Carl Heide's phrase that discovered this in the H1 emission. And the answer that he gave for those structures is, most likely, these are superbubbles that pop up. When the bubble reaches the scale height of the plane, it depressurizes, you blow the roof of the cloud, and then all you left are the sides of that bubble. Okay? He called this worms or chimneys, and that has a name that has been sticking around. For the horizontal filaments, you kind of see that you can naturally produce them in a simulation of a galactic plane. This is the work of Rowan Smith, where she's simulating a galactic potential, and she sees that you can stretch filaments very efficiently if you control well the supernova. So this is dominated by the potential. Here you have random supernova. If now you put feedback, you become very efficient at blowing stuff off the plane. Actually, to the point that if you don't place your supernova correctly, it's very difficult to reproduce the scale height of the disk, as we know. But if you put too much feedback, then you start blowing everything away. So most likely we're somewhere in between. We're not completely dominated by feedback. We're not only dominated by the potential. And we have another ingredient, magnetic fields. What the magnetic fields do is they keep coherent the filamentary structure. So we know that if these bubbles explode in a magnetized medium, the edges of the bubble are preserved by the magnetic field, and there's less fragmentation of those filaments. This is a simulation by Philip Kirihidis, in which he reproduces that in 1 kiloparsec, in a 1 kiloparsec box. So here you see density, temperature, column density, ionized hydrogen, and then in the fifth column, you see the atomic hydrogen emission. So I'm going to play it again, so you can focus in the fifth column. Then you see how each supernova is blowing material off. And if you have enough supernova, you become very efficient at blowing material off the galactic plane, and you're left with holes in the disk and vertical filaments above and below the disk. So we think that this is what we're seeing in the inner galaxy. And in the outer galaxy, it's less likely that we see so. So this is what we see, mostly perpendicular in the inner galaxy, mostly parallel in the outer galaxy. And that is in agreement with kind of the distribution of supernova bubbles. Kind of hard because this is not a complete catalog, but for sure we know that something is changing with galactocentric radius. We have less star formation, we have less massive stars in the outer galaxy, and that would explain why the galaxy is less efficient at lifting material in the outskirts beyond 15 kiloparsecs. Okay, so what have we been doing lately? Well, if this is the case, if red is mostly horizontal and blue is mostly perpendicular, this has to be correlated with something else. And we look at the catalogs of star formation. So these are all H2 regions traced with radio recombination lines. Radio recombination lines are transparent to the disk, so you can see even the other side of the Milky Way. And you can fix the sensitivity such that your catalog is complete for O stars, so for massive stars. And I'm going to blink back and forth. And then we're going to stay here the rest of the day until I convince you that there's a correlation. No, there's a correlation between the places where you see mostly vertical filaments are the places where we see high mass star formation, even in the outer galaxy. So to summarize, we see that profile. Filaments have a tendency to change their orientation. So what is left to be done? Well, we can compare with the CO, with the molecular material that is formed inside. So the CO disagrees with that. In the places where we see mostly vertical filaments, the CO is actually mostly parallel to the galactic plane and is constrained to the plane. The scale height of CO is also lower, to the point that even when you see it at high resolution, that big patch that we saw, most of the vertical filaments in CO is imperceptible. You see the CO aligned with the magnetic field, with the galactic plane, sorry. My conscience betrayed me. So here, for example, is, again, V. So you have filaments that are very horizontal, and the CO has no preferential orientation. But you also have some filaments in CO that are very horizontal, and then there's no preferential in the CO. The H1 and the CO are not correlated, so you're not inheriting the orientation of the H1 filament into the CO. So I'm about to finish. This is reminiscent of something that we found in the Planck, in the studies with Planck. We found that actually molecular clouds tend to be perpendicular to the galactic, to the magnetic field. So you have a change with column density from mostly parallel to the magnetic field to mostly perpendicular. This is one of the things that can be acting on that. I can comment on that later. And there's also feedback. There's the fact that you form molecular clouds, but the molecular clouds don't necessarily inherit all of the properties of those shells that you're blowing out. This is the Orion Eridano superbubble. This is one of the most nearby examples of supernova feedback. This is at the front wall of the bubble is at 100 parsecs from us. And this is like this big in the sky. So tonight, if there are no clouds, you can check the Orion constellation that is up here. And that's where actually some of the most famous molecular clouds are sitting. So I'm going to wrap up there because I'm running out of time. We're also looking at the H1 around molecular clouds, but I'll leave you with my conclusions. So basically, we see what we think is the imprint of feedback with galactocentric radius in the structure of atomic hydrogen. That structure of atomic hydrogen is not inherited by the CO clouds that we also see towards the galactic plane. And the goal now is to use this anisotropy that we found in the H1 to find the amount of material that we're lifting off the plane and quantify the amount of gas that is not available for star formation in the plane, and also the amount of gas that is bringing back into the galactic plane. Thank you.